Our next speaker is Gabriela Gomez from University of Strathclyde, and Gabriela's work came to us because we saw all these sorts of things that we could add to our TB models and other models in terms of risk factors. And when we look back at the literature, Dr. Gomez has really been doing decades of work in this area to kind of show theoretically what happens when you have lots of different kinds of risk that you need to account for in your model. So very excited to have Gabriela here today. Gabriela, go ahead. The floor is yours.
Okay, thank you, Stuart. Okay, so for this talk, I'd like to focus on some relatively novel concepts in disease modeling. So I'm not going to, these models won't have the specificities of TB, and that because I wanted to make the models as simple as possible to get the key ideas across. But it's all about taking into account risk variations, so the heterogeneity and susceptibility in models, in disease transmission models, and to show how impactful that is and how important it is to take care of that. So, when we have variation, when variation in susceptibility is accounted for, we find that we systematically estimate reproduction numbers to be higher, and we predict the impact of uniform control measures to be low. So if there is heterogeneity in the real system and we don't incorporate that in the model, we are going to underestimate the reproduction numbers, and we are going to overpredict the impact of interventions, because interventions seem to have higher impact if the reproduction numbers are lower. So the two things are not independent. So first we start with an SI model, and we introduce the idea of selective depletion bias. So we have a population of susceptible individuals. X is the susceptibility factor. So it can vary in a continuum, or it can be discrete, but the idea is that some individuals are more susceptible than others. And because of that, that little x appears here, the susceptibility factor appears here, and this is the force of infection. So the force of infection so it's the per capita rate of infection for an individual, and that depends on the susceptibility level of that individual. So individuals with a higher X are more likely to be infected. And that's how heterogeneity appears in these models. And of course, this integral here means that individuals of any susceptibility level can infect any other individuals irrespective of their susceptibility level. So that's the force of infection, and this is susceptibles being depleted, and this is the infections accumulating over here with this equation. And this is for simplicity an SI model, so there's no recovery. So what we find with these models is that if it is an infection that is just invading a population, we have with the homogeneous model, if we assume variance 0 for the susceptibility distribution, we have infection propagating in the population in this toy model. And if we include a susceptibility distribution with a variance of 10, I think I did in this case, the growth curve for infections is very different. So it can reach the same endemic equilibrium, but it needs a much higher R0 in order to reach the same endemic equilibrium. And the reason is that when we have a susceptibility distribution, we start the two models, one homogeneous and one with a variable susceptibility. The individuals that get infected first are not random individuals. They are individuals with a higher susceptibility, individuals here at the tail of susceptibility distribution. So as a result, the susceptibility distribution starts with a mean of 1, as we normalize here, starts with a mean of 1, but the mean of susceptibility for those individuals that remain infected, that remain susceptible, in other words, didn't get infected yet, becomes lower and lower because of this selective depletion of the more susceptible individuals. And this is shown here. So after some time of transmission, we get that the mean susceptibility in susceptible pool is now 0.2 at the end of this simulation, while at the beginning was 1. So because of this, the growth curve, the growth in the infection curve decelerates for the same R naught. So actually, if we ran the model with the same R naught with the heterogeneity, it would only grow up to here because of this depletion of the most susceptibles and the decrease of susceptibility over time. So in order to counter that, we need to boost the R naught so it can go to the same, can reach the same endemic equilibrium. So now we assume that we are at endemic equilibrium, and now we suppose that we have an intervention that reduces susceptibility of everybody by the same factor for everybody, could be by vaccination or some other intervention, and that will have some impact under the homogeneous model, and it will have lower impact under the heterogeneous model. So if we use the wrong amount of heterogeneity in the model, we are going to get wrong predictions. So that's sort of the core idea that is going to be present in the rest of my talk. If we have an infectious disease that it's not endemic, but it's more like just an epidemic, we build the model in a very similar way, and we have suppose that now our 0 is equal to 3. With a homogeneous model, we have this black epidemic curve. If we include heterogeneity and susceptibility with a certain variance, we get this blue curve. So I'm not going to talk more about epidemic models, but I just wanted to show that the results are consistent when you change specificities of your model. And if instead of doing heterogeneity in susceptibility, you do heterogeneity in connectivity, like some individuals are more connected, so they are more likely to acquire infection, but also more likely of transmitting infection to others, you get the same phenomenon. You'd get this green curve because of selective depletion. So that was background. So, but in this talk, I'd like to talk about how do we estimate these distributions? How do we know how much variance to put in our models? It is important, but we need to be able to estimate it. So, and I'm going to present some ideas of how we could go about generating this. Although from Peter's talk, we may just having data on nutrition or HIV status may actually account for a lot of the variation, but there may be other sources of variation that we have not measured. And given how important it is to get the whole heterogeneity of susceptibility included in the model, I'm building these models with generic distributions where I'm not specifying what the risk factors are. I'm assuming that I cannot even measure the distributions directly, and I'm going to try to infer them indirectly. And taking these distributions as part of the modeling process, like other parameters. So, and the way I think we may be able to get the way I think we are able to get these inferences of the distributions is by having stratified data. So it could be observational data stratified by region or something else, doesn't need to be region, or experimental data and we can conduct the experimental studies in a stratified way that will enable us to infer the susceptibility distributions. And the idea is that if we have a region where intensity of transmission is higher, selection is stronger. So the distribution has more impact on the output of the model. If we are in a region where transmission intensity is lower, then that selection and depletion of the most susceptible individuals is going to have less impact on the outcome of the model. So if we have regions of different transmission intensities, we are kind of able to reconstruct the susceptibility distribution. So suppose that we have individuals of low susceptibility and individuals of high susceptibility. The susceptibility factors are here, alpha 1 and alpha 2. And suppose that we have a meta-population model. Actually, I felt very much the urge of developing this model in response to some reviewer of a paper I wrote some years ago, and that paper was actually about TB. Where the reviewer said, but why are you making your model so complicated with these distributions? Why don't you just do a meta-population model with a region of different regions have different transmission coefficients, different transmission rates? And here I did this to show to that referee that it really matters. It's not the same thing. What we get with individual variation is actually can be quite different from what you get from a meta-population, a classical meta-population model. So suppose that you have these individuals and so a meta-population model more or less assumes that high susceptibility individuals are in one region and low susceptibility individuals are in the other region, but you have homogeneity within region, usually in the meta-population models. Here I'm assuming that you have the same number of high susceptible individuals and same number of low susceptible individuals, but you distribute them in a different way. Don't put them all light blue in one region and the dark blue in the other region. Just, of course, you have the higher transmission region with more high susceptibility individuals, but there are also some high susceptibility regions in some high susceptible individuals in the lower transmission region. So this model, it's how it's written. I unfortunately I forgot to put here the reference for the paper where I actually introduced this model in response to the reviewers, but I'll be able to share it with anyone. If you are interested in the paper, just email me or something. I'll be able to share the paper. And I'm also writing a more theoretical paper about this, so it should be available sometime soon. So that's the equations for what I've just said. So the distribution of one region and the distribution of the other region. Of course, there are more high susceptible individuals in the high transmission region. And what you get with these models is that so you can solve these models, and basically you get you suppose that you control the population of high risk individuals in the low transmission region. Could be another of the parameters. So basically here I'm controlling what's the proportion of high susceptibility individuals in this region, and that's a parameter here. And then I can actually calculate, I can get the exact solution for this problem, and I can calculate the prevalence of infection as I vary this parameter. So of course, in the low transmission region, the prevalence goes up as this parameter increases, and it goes down in the low transmission region. So these are the distributions at this end of the larger plot. So region A is homogeneous and region B is homogeneous, but they have different risk factors. And this is what a classical meta-population model would do. And this is the new model where at the end of this range of validity for this parameter, the distributions are equal, so the curves coincide there. And this is just a simulation of running the model with those parameters. At the left end of the plot, you'd get this growth curve for infection, for the total population, and for the two subpopulations, and here the whole thing would coincide. But more interesting is when you try to solve the inverse problem. Suppose that you are given the prevalence of infection in region A and in region B. This is IA and IB, which I assume here. And now you have these parameters, so the proportion high risk in region A, and you fit the model. In this case, you can actually get exact solutions, so it's not a statistical fit, but so it's solving the inverse problem. So when you have the two homogeneous regions, you estimate the variance to be so at the end the variance would actually be zero. These would converge to the same factors alpha 1 and alpha 2, but on the right you get much larger variances, and this is the maximum variance you can get for this setup, and the basic reproduction numbers are much higher. So if you had naively used a classical metapopulation model to estimate R0A and R0B for those models, you'd get those values around between 1 and 2 in this case. But if you had used the more mixed model, where the high-risk individuals are distributed in a different way across the two regions, you get much higher, you'd estimate much higher R0. So that's what this is showing here. So this is the growth curve of infection for the classical metapopulation model and for the model I'm introducing here. And now you apply an intervention, just like in the first model I showed. You apply an intervention to reduce susceptibility by half. So here you'd get the intervention will have a great impact. And in the other model, it has much less impact. So, but both models could fit the pre-intervention incidences in the two regions. So it's really important to be able to distinguish between which scenario we are, because we may have created great expectations for this intervention, and then we apply it in practice, and it's disappointing. So, so that's the result here. Now, just very briefly, I know that I don't have time to talk about this. So I talked about trying to get estimations of R0s as well as the variances of the risk distributions using observational data, stratified in ways that are suitable for this purpose. But we can also do that from observational studies. Here is vaccine studies. One finding that we see, all the vaccines I show this. So this is a BCG vaccine. This is a rotavirus vaccine, a malaria vaccine. So and you look at trials that where the efficacy of these vaccines are estimated, and systematically you see that in regions of high transmission. So this horizontal axis is a measure of intensity of transmission in the particular regions. In the regions of high transmission, the efficacy of the vaccine is estimated to be lower, and this can be quite a big drop in efficacy as you go from low transmission regions to high transmission regions. And I think what's happening here is actually this drop. So this drop in efficacy from these maximal values that you get in the low transmission, this could be due to selective depletion bias, like I described before. So I realize that there's. I don't have time to show these models, but I just want to flag here that they are very similar. I use this susceptibility. I analyze trials, in particular these multi-center trials with models that have these susceptibility distributions in them, and I can get these curves that could fit this series of data points and this decline of vaccine efficacy as the intensity of transmission increases. So, and just one more slide, and to show that this can also be done with these more modern challenge studies. And here we have dose of challenge as proxies for intensity of exposure. And we use those response curves, again, fitting models to those models that have these flexible distributions in them. We fit them to those response curves in order to estimate the parameters that describe the distributions. So we've done this for fish studies in insects, fruit flies, and mosquitoes, where instead of vaccines, we have Wolbachia, which also reduces susceptibility. And we were able to successfully estimate these distributions. And we are now starting to collaborate with clinical colleagues who do human challenge studies, and we're trying to apply the same ideas there. Okay, so I'm finished. So this is my last slide. So as I said, selective depletion bias applies generally. This is not only about infectious diseases, it applies more widely. And in ecology, evolution, models usually do not take this selective depletion bias into account. So we are actually starting to do this beyond infectious disease modeling as well. And remodeling selection is a novel approach to infer an observed variation from its effects on observational or experimental data collected over selection gradients. Okay, so thank you very much for your attention. I'm happy to take questions now or later, or by email or whatever.
Great. Thank you, Gabriela, for that very provocative talk. Always very interesting ideas that you present. Open the floor to any quick questions. I know we're running short on time, but Gabriela, maybe okay. Yep. One quick question.
So the alternative explanation for reduced efficacy of vaccines in the presence of high exposure could be, I mean, one could be is just there's multiple exposures and the vaccine typically is estimated, per average, say, exposure. Second, it could be immunosuppression. Just vaccine doesn't work as well as when you have like malaria vaccines, when you have a lot of exposure to malaria, immunity might be. There could be other explanations. So how do you discriminate between what you propose and is the mechanism versus, well, I just named two?
Yeah, absolutely. There can be other explanations. And but also what I'm proposing is something that cannot not be present as well, because there is variation in susceptibility, and we know that whatever model we write, when we include these variations in susceptibility, we have this selective depletion of the most susceptibles that creates these effects. So the question is, how do you quantify how much of these trends are due to what I'm proposing and how much is due to other things? So I think I think I'm just proposing another explanation to add to the other existing explanations, which and as far as I know, there is a difficulty in a general difficulty in explaining the magnitude of these trends. So maybe it suggests to me that maybe something is missing in the existing approaches, and this could be the part that, or a large part in what is missing.
Okay, great. Let's think. Sorry, there are more questions, but Gabriela, if you can stay on, and any other questions, please drop them in the chat. Let's thank Gabriela one more time for that very interesting talk.